sorry. The title of her talk will be The Tangled and Knotted Tale of Two Graphs.
Hello everyone, thank you for inviting me to speak today. I'll be speaking about the research I did at Denison University under the Anderson Research Endowment with my advisor, Dr. Lou Ludwig. Today I'll be talking to you about the history of the question that I looked at and some of the motivation behind why I looked at it. Then I'll be going into the work that I did and some of the results that I've found thus far. And then I'll be continuing with some of the questions that my research has left me with, what I hope to continue throughout the school year as I continue this research. And before I start, I just want to let you know about what some of these terms that I'll be speaking about mean. The first is a knot. Now, a mathematical knot is pretty similar to what you know as a knot. If you take a piece of string or some other string-like object, and you tangle it and twist it up, and then take the two ends of that string and attach them together. Now, it's very important for a mathematical knot that it be a closed loop, so the knot in your shoelace isn't really a knot mathematically. You get this knot, so I can't untangle it to make a circle, which is known as the unknot. Now, the knot that I just made and the knot on the screen are the same exact knot, even though you can't be able to tell that really. It's what's called the trefoil knot, and it's the simplest non-trivial knot. So that'll come up a lot throughout the talk. The other term that I had is a complete graph. Jeff kind of just explained that, so I won't go over it in too much detail. But just for a review, it's a graph with n vertices, referred to as k sub n, such that every vertex is connected to every other one by edge. And here, the numbers around the edge are the degree set that Jeff talked about previously. Some of the history behind this, my research, the motivation behind the research, kind of started 14 years ago. In 1983 and 1984, Conway and Gordon, and then independently Sachs, came up with a kind of groundbreaking result in graph theory. And off of this, what they found, the result that they found, a lot of research has been generated up to the research that I did this summer. Well, what they found was that K6, the complete graph of 6 vertices, which Jeff was talking about earlier, is intrinsically linked. So no matter what embedding or projection of a graph in space that you have, no matter what it looks like, as long as there's 6 vertices and they're all connected to each other, you're always going to have at least one linked pair. This is a special embedding of K6. There are 10 disjoint pairs, but only one of them is linked, and that is outlined in red right there. Now, Conway and Gordon showed something else in 1983, and what they showed is that K7, the complete graph on 7 vertices, is intrinsically knotted. So no matter what embedding you have, you're always going to have at least one knot. Now, I've highlighted the knot on this embedding of K7 here, but you can't really see it. So I took it out for you. And this is actually our friend the trefoil knot again. So you can see the knots have lots of different patterns and ways they can be put in space. Well, this was a huge result. It basically showed that you could have complete graphs that were always linked, always knotted, and people got really interested in complete graphs and linking and knotting. Well, 10 years later, in 1993, Robertson, Seymour, and Thomas came up with an even bigger result. What they did was they categorized intrinsic linking. So for any graph that was intrinsically linked, they categorized exactly the way it had to be. And this was huge. They said that a graph is intrinsically linked if and only if it contains one of the Peterson graphs as a minor. Now, a minor of a graph is a graph that's found from the original by triangle Y or Y triangle exchanges, which is it's similar to a subgraph. So we'll just leave it at that. This is a family of Peterson graphs. This is what's traditionally thought of as a Peterson graph. This is a whole family of them. And if you look over here, this is our friend K6, which we know is intrinsically linked by Conway and Gordon and Sachs independent result. So this was a huge result. And you might think with such a foundational result, people might stop there. Okay, we've characterized intrinsic linking. We don't need to research anymore. But mathematicians don't want to stop, so they've specialized it. And what people started to do was looking at linking and knotting even more complex structures and specializing the results. So some people have been looking at embeddings containing 2 disjoint links. There are groups of people working on 3 or more components, and then there are researchers such as myself who deal with straight edge embeddings. Now, a straight edge embedding is exactly what it sounds like. Between the vertices, there's only straight lines. They can be expanded or contracted, but they can't be bent in any way. My particular question came from a workshop with Colin Adams in 2004, and there are two questions were posed. The first one was how many linked components occur in a straight edge embedding of K6. We know there has to be at least one, how many. That work has already been done with Colin at Denison University, and others have found similar results. The second was the one that I looked at. A straight edge embedding of K7 has 360 Hamiltonian cycles. How many of them are knotted? So how many knots are there in a straight edge embedding of K7? A Hamiltonian cycle is actually a closed loop that we need for a knot. If we look over here, this is an embedding of K7, kind of small, but if you start at one vertex, you travel along the edges and visit every other vertex, and you return to the one you started at, closing the loop, that's a Hamiltonian cycle. So in every embedding of K7, there are 360 possible knots. Now why straight edges, why are they even interesting at all? Well, actually, it's because of chemistry, because of chemists who are not theory all started in chemistry. Then mathematicians got interested, and finally molecular chemists are interested in knot theory again because they found knotted molecules. This is the simplest knotted molecule, again it's a trefoil knot. But if you look at the bonds between it, you can see that the bonds are almost straight. So chemists are interested to see how straight edge knots behave so they can figure out how knotted molecules behave. But before I could go over this, I had to think of what kind of knots I was looking for. And there's only two types of knots that can be made with 7 or fewer sticks or straight edges. The trefoil knot, which actually only needs 6 sticks, and the figure 8 knot, which needs 7. The other thing I had to look at was how I was going to classify the embeddings of K7. I did that, like Jeff talked about, there are 5 different degree sets, such that all the vertices are on what's called the external convex hull. And for simplicity's sake, we just labeled them K7-1 all the way through K7-5. What I started with was K7-5 because the structure was well known. My advisor had some trouble with it the year before, so he researched a lot with his student, and they found out what exactly it looked like. There's only 2 types of vertices, degree 4, so 4 external edges connected to it, and degree 5, 5 external edges connected to it. And I actually have a model of the graph right here. This is half of the graph. These are the degree 5, the blue ones, and the degree 4, the red ones. And the interesting thing about it was the internal structure. You can see the blue lines. These are the edges between the degree 4 vertices, and they make a star. So then there's one more internal edge connecting the 2 degree 5 vertices, and that can puncture anywhere in this pentagram structure. And where it punctures really became crucial depending on where the knots were. Now, the other thing about stars, I don't know how well you know how to construct stars, but in every point there's what looks like the letter A if you remove the other edges. Well, in every star there's going to be one that I labeled the special A, and it's special because one of the legs of the A goes over the horizontal edge and one underneath. Now, that only happens once in any kind of star. Why this is important is because for the trefoil knot and the figure 8 knot, they're both what we call alternating knots, which means the crossings in the knot need to be alternating under and over and so on. The trefoil knot needs 3 alternating crossings and the figure 8 needs 4. Well, here in this A, we already have 1, 2 alternating crossings, so all we need is at least 1 more. That's a necessary but not sufficient condition for a knot. Well, I looked through all the cycles, and 360 is a lot of cycles. So what I did was I separated the cycles into categories based on how many internal edges there were in each one. So if we traveled around in our cycle and went through one internal edge, we would have 90 different cycles at that point. So if we look at my result, we can see that you could have anywhere between 6 and 10 knots. And it really all depends on where this edge between the 2 degree 5s punctures. If you puncture right through the middle, you get only 6 knots. But if, for example, if you puncture in this yellow region over here, this is over here, you can get actually 1 figure 8 knot, where all the other times you'll get a trefoil knot. Well, for K7-1, which is the next one that I did, I also separated the number of cycles based on the internal edges. But as I was looking at K7-1 and its structure, I actually found out that K7-1, as you can kind of see, also has a star in it. I lost the big one, so the little one will have to do. So I thought that the star was the same star that appeared in K7-5. In fact, the only difference was this red edge right here. The one between the 2 degree 5 was different. For K6, what we have is a straight edge between the 2 degree 6 vertices, and it's actually an external edge. But if you were to move that edge on the internal, it would become a graph of K7-5. That was the only difference. But I looked at my results and I found that almost all the knots needed that internal edge between the 2 degree 5s, except for one. But it did use that special A. So if you look, there's already 1, 2, 3, 4, 5 vertices used in that graph, so you can connect it to the other two, which happen to be degree 6. You get a triplet in that. So there are knots in case 7-1, which I was excited to find out. But it turns out, out of all 360 cycles, that's the only knot that there is. There is only one knot in case 7-1. So Conway and Gordon, when they said there had to be at least one, were just barely correct, which was incredible. So I'm going to continue this work into my senior year, and I'm going to look at naturally K72 through K74. And I'm hoping that that similarity between the structures, or maybe only one edge is different or one crossing is different, will come up again, so it's a lot easier to count the knots. I want to thank you for having me here today, and I'm going to thank the Anderson Research Endowment and my advisor, Dr. Luke Ludwig, for the help that they gave me.
This paper is now open for discussion and questions. Sean?
Do you have any intuition as to whether you can kind of go the other way? Take a graph, look for the special A, and then induce how many knots and stuff are in there?
I could. I'm afraid that I would miss some of the knots. I'm not sure that this star structure happens in every one of them. I think it's only in these two. It's actually because of the subgraphs. If you take one of the vertices away, you get K6, and one of them has a knot K762. So I did kind of do that for K7-1. I looked for the A, and I could see that there was a knot there. I could, but I wanted to make sure that I got all the knots, so I separated and looked through every cycle. Not really individually. Yes.
I was just wondering, because my main area is chemistry.
Okay.
If as you can continue your work in the future, are you thinking about like pairing up with a person in chemistry? Because I can see some applications like with the buckyballs, the Buckmeister fullerenes, and some of the things we see in protein structures and those kind of things that a person with that knowledge background could maybe see some application.
Yeah, I've thought of that. I think it would be really neat to work with a chemist. I don't know too much about chemistry. We probably won't be, but I'm hoping that if I do publish a paper, someone in chemistry might be able to use the results.
Oh yeah.
So.
We have a question
I
next.
was just wondering, one of your earlier slides had that family of complete graphs. I was wondering, there were different notations. There were some G's and P's. I was wondering if those were something different, or it's just
These?
it was even earlier.
The Peterson graph. Yeah, they're actually found by, like I said, there's different exchanges. A triangle Y is basically if you have 3 points, and you put an extra vertex in the middle, and the triangle becomes a Y. And so you can kind of see some of that here. So these are all in the same family of graphs. You can just change some of the edges using those exchanges. So they're very similar graphs. So they have the same characteristics. I don't know exactly why they're labeled the way they are. But for example, K44 is when you take, there's 4 vertices at the top and 4 at the bottom, and they're connected from the top to the bottom, but not to all to each other.
Okay, let's thank our speaker again. Okay, so it's time for a 10-minute break, so I invite you all to take a break. And why don't we say at 11 o'clock, we'll resume. Thank you. Nice job.